all familiar with Moore's Law, right? It's the thing where we all get twice as much good stuff every 2 years. Almost for free. Twice as much speed, twice as much functionality for our designs, and twice as much power efficiency. Sounding pretty good, isn't it? We can all do our big happy dance and... Oh, wait. Apparently, we also then have twice as much complexity with twice as many gates to verify in our sign-off timing analysis. Ouch. That part just isn't as fun. We need a way to speed up timing analysis pronto. Hi, I'm Amelia Dalton, host of Chalk Talk. Timing analysis is chewing up more and more of our design time these days, and we need a solution that works better than just throwing some more computer power at the same old tools. My guest today is Ruben Molina from Cadence Design Systems, and we're going to talk about a new approach to hierarchical timing analysis that should really help us break out of this bottleneck. And before we get started, remember to click that link. There you can download a free white paper called Hierarchical Timing Analysis, Pros, Cons, and a New Approach. Hi, Ruben. Thank you so much for joining me today.
Hi, Amelia. It's nice to be here.
So, we talked before in a previous Chalk Talk about sign-off timing analysis. Now, it's really exciting that runtime and capacity are no longer issues for design teams, right? Solved.
Yeah, that's true, but there's still a few... There's still a few areas that are pain points for users like you, and come up with some new techniques to address those problems.
Absolutely fantastic. So, abstract and conquer. What's up with this title, Ruben?
Well, that's a play on, of course, divide and conquer. When you look at the way that people do really large designs today, they do it in what we call hierarchical analysis, where basically they're dividing the design up into several pieces and then running those pieces individually.
Sure.
There are limitations with that, which we're probably going to get into here in a few minutes, but abstract and conquer is kind of a new way that we're doing things where we're really doing kind of flat level analysis, but we're doing it on targeted areas in the chip that need to be analyzed. So it's really kind of the best of both worlds.
Okay, cool. So you and I talked about Tempest last year, right?
That's right. Tempest was a new product that we introduced at DAC in 2013. And one of the reasons why we introduced it was because designs at 28 nanometer and 20 nanometer were becoming larger, and the overall static timing analysis and design closure phase was really starting to consume most of the design cycle. And so the tools that were on the market at that time really weren't trying to address that increasing design cycle phase.
Sure.
So we introduced Tempest, and Tempest was really focused on three areas. One was obviously performance, to try to get this part of the design cycle down.
Sure.
Accuracy, because it's a sign-off tool. If you're not producing the correct results, then nobody really cares.
Right.
We used to have an old joke in the industry that when tools came out and claimed that they were 100 times faster, it was always, 100 times faster to the wrong result.
Right.
So of course, accuracy is a big deal. All sign-off tools require it. And then the last part of Tempest is really this closure aspect where it's not enough to just analyze the design. You really have to close all those last remaining violations and do it with sign-off quality results.
Right.
So that's what Tempest was focused on. I have to say that in the last year, it's been hugely successful. We've gotten a lot of people interested, and a lot of people have actually bought into it and are starting to use it in their designs today.
Excellent. So, Ruben, you guys aren't reinventing the wheel here. Wasn't it working fine already?
Well, there were techniques for trying to address these capacity and runtime issues in the past, but they were always with some kind of limitation.
Yes.
And basically, there were really two kinds of hierarchical analysis. The first one was through the use of what they call extracted timing models, or ETMs. That's normally what they're referred to. And this is basically when you take a block of logic in the design and you create a timing model for it.
Yeah.
Once you do that, you've really looked at the behavior of this block of logic at the boundary of the block. And you've kind of thrown away all the stuff that's inside. You're trying to model it just at the boundary pins.
Sure.
This is really good for capacity because now you've just got a simple timing model instead of maybe 500 or 1,000 cells.
Right.
But the problem with it is you're really missing a lot of the in-context effects. So in-context effects means that when you place this block at the chip level, at the top level, there are impacts from top-level logic onto this block.
Right.
And those kinds of things are not able to be perceived when you're creating the timing model.
Right.
Because the
okay.
timing models are all created before you've instantiated it into the top level. So though it's good on capacity, probably the least accurate in terms of analysis.
Yeah.
And when we talk about the best accuracy for analysis, really it's flat level analysis where you're able to kind of see everything in the chip all at once.
Right.
That's really the holy grail of accuracy.
So, Ruben, there's got to be something better, right?
That's right, yes. We did the ETM thing for a while, and then some smart people came up with this concept of interface logic model, or ILM. And what the ILM concept was, let's only look at the paths that go from the top level through the boundary of the block you're looking at,
Yeah.
and then they go all the way through to the first sequential element.
Aha.
And let's
okay.
just abstract that out, and let's create part of the design which includes the top level and this abstracted piece.
Gotcha. Okay.
So think of it as kind of like a donut, and in the middle of the donut is some register-to-register logic that we're basically eliminating.
yeah.
But everything going to the first register or starting from a register and going out of the block is going to be seen.
Okay. Okay.
So it really improved on the interface timing.
Makes sense. Yeah.
But again, there's still this element of over-the-block routing or in-context effects that may actually impact these register-to-register paths
Right.
within the block, which aren't seen now because we basically eliminated that.
Yeah.
And from a capacity standpoint, it's better than full flat analysis because you are carving some of it out and kind of throwing it away, but not as high capacity as ETM. So the more accurate you get, it seems, the closer you get to flat, the kind of less capacity you're getting because
Right.
you're including more and more logic. So it's kind of a whack-a-mole.
Oh, great.
You know,
okay.
It's like, let me whack this mole down. That's capacity. And then what pops up is the inaccuracy issue.
right.
Knock that down, and now you've got a capacity problem again. So people have been trying to come up with a way to address both of these issues.
So, are there other things that people are doing as well?
Yes, there's been another approach recently. It's probably been on the market maybe for 2 or 3 years now. It hasn't particularly taken off very well because there are some limitations to it as well. But in this third approach, you, as the user, would basically take all your logic blocks and you would pre-time them.
Okay.
And you would create a timing database for each of your blocks. And then at the top level, you would read these timing databases in, and the overall timing analysis would be done flat at the top and utilizing the timing databases that were pre-timed.
Okay.
Okay, so from that standpoint, capacity is good.
Yeah.
The problem with it is that, again, at the block level, you're basically timing this block based on some assumptions about
Right.
what's happening at the top level.
Yeah.
At the top level, now, you're basically timing top level flat, and you're utilizing a database at the block level that was based on incorrect
Right.
top
yeah.
level assumptions. So what has to happen in this approach is that you basically time the blocks, preserve the timing databases, then use those at the top level, time the top level, refine the constraints after you've done the timing, redo the block level using these new constraints,
Yeah.
then save the databases. So it's an iterative approach. And I think what most people have found is that though it's good on capacity, it's just a lot of work, and managing the constraints at the boundaries is a big issue. And so I think with the increase in the capacity of compute servers today, they're like, you know what, I'm just going to try to run it flat.
Right.
And tools like Tempest have enabled people to do that. But still, not everybody has a 1 terabyte
Right.
32 processor machine
Yeah.
that they can do this. So for those that are limited, it's still a problem.
All right, Ruben, throw me a bone here. You must have a better solution because these all kind of suck, right?
You know what, Amelia, just for you, I've got a special thing here.
All right.
Okay. So we have something called scope-based analysis.
Okay.
Okay. And really what it means is you define the scope of the analysis. So
Okay.
let's say you have a block.
Okay.
And let's say you have a large SOC.
All right.
Okay. Let's say it's 100 million instances. And if you were to run that design flat
Yeah.
in Tempest, it would probably take you 3 or 4 hours to do.
All right.
Okay. But in other tools, it might take you 10 or 12 hours.
Yeah.
Okay. So now you changed one block in that design, and maybe that block's only like 1 million cells.
All right.
Okay. It's not 100 million, it's just 1 million. Now today what would happen is you'd either have to run, once you instantiate that into the top level, you'd have to run the entire design flat.
Right.
So you have to run 100 million cells.
Yeah.
Okay. But really only changed a million.
Right.
So why run 100 million? Or you would have to create one of these hierarchical models, and then there would be the limitation issue.
Right.
Okay. So what we've done for you, Amelia, just for
Hey,
you.
okay.
Okay. We've created the scope-based analysis where now you tell Tempest, I want to analyze just this block, and I want to do it in the context of the entire chip.
Oh,
So what happens is Tempest abstracts just that block logic and all the logic that that block communicates to at the top level.
okay.
And this is where we talk about abstract and conquer.
Yeah, yeah.
So now what happens is instead of running on 100 million instances, it's a million cells that you've changed, plus it's whatever this block communicates to, which could be a few million additional cells.
Yeah.
And in essence, what we have is a part of the design which we're going to analyze full flat so we see all the context.
Ah, okay. Yeah.
Okay. And the result is something that is equivalent to a full flat analysis.
Yeah.
So there's no compromise in accuracy. The only compromise is you don't have to wait so long for the
Nice.
result.
Yeah.
Right? And you can run it on a smaller server too. You don't need that 1 terabyte machine with the 32 processor cores. You can just
Right.
run it on one of your everyday servers you have in the farm.
Excellent.
It could be a 128 gig or a 64 gig machine.
Yeah.
So this is the new way to do analysis that increases capacity and dramatically reduces runtime.
Fantastic. All right, let's circle back a little bit and recap, if you don't mind.
Okay, sure. So Tempest was designed and announced last DAC to address this growing issue with static timing analysis runtimes and capacity and also design closure.
Yeah.
It's been hugely successful, and now we've introduced something to address this issue with hierarchical analysis limitations. And what we have is something called scope-based analysis, which actually does an on-the-fly abstraction of the block that you want to design,
Yeah.
plus all of the context around that block.
Excellent.
And the run times are dramatically reduced. You can run on smaller capacity hardware, and you get the same results as full flat.
Fantastic. That sounds great. Sign me up.
Okay.
Well, I think that's all I have time for. Thank you so much for joining me, Ruben. It's always a pleasure speaking with you.
You're welcome. Thank you.
Also, before we go, don't forget to click that link. There you can download a free white paper entitled Hierarchical Timing Analysis, Pros, Cons, and a New Approach. For more Chalk Talks, check out EE Journal's YouTube channel or the EE Journal On Demand archive.